everyone, welcome to CyberNexus, your hub for cybersecurity. Let's get started. Today we're starting with networking fundamentals for cybersecurity. You might wonder, why networks? Well, understanding how computers communicate is the backbone of cybersecurity. If you want to protect systems, you first need to know how they connect and share information. So let's dive in. Alright, let's start with the most basic thing. What is a network? So basically, a network is just devices connected together to share data. Think of it like computers having a conversation. They send messages back and forth so everything works smoothly. That's the core idea behind any network. So, networks come in different types. One common type is a LAN, or local area network. It connects devices in a small area, like your home Wi-Fi or an office network, so they can share files, printers, or internet connections easily. Another type of network is a WAN, or wide area network. Unlike a LAN, a WAN connects multiple LANs across cities or even countries. This is perfect for big organizations that need their offices in different locations to communicate seamlessly. And finally, we have the Internet, the biggest network of all. It's basically a massive WAN that connects millions of LANs and devices worldwide, letting us browse websites, send emails, and communicate across the globe instantly. Next, we're going to talk about IP addresses and the different types of IP addresses. So what exactly is an IP address? Think of it like your device's digital home address. It helps computers and other devices find each other and communicate on a network, making sure data gets to the right place. Now let's talk about IPv4 and IPv6, the two versions of the Internet Protocol that give every device its unique address on a network. Think of it like this. Just like every house needs an address so mail can reach it, every device on the Internet needs an IP address so data knows where to go. Let's start with IPv4. IPv4 uses 32-bit addresses, which look something like this: 192.168.1.1. It can support around 4.3 billion unique addresses, which sounds like a lot, but with billions of devices around the world, we eventually started to run out. That's why a new version was created, IPv6. Now IPv6 uses 128-bit addresses, which look more like this: 2001 DB81. It provides almost unlimited IP addresses, enough for every device on Earth, and even more for the future. Plus, IPv6 comes with built-in security and auto-configuration features, making it smarter and more efficient than IPv4. So in short, IPv4 is older and limited, while IPv6 is the next generation, built for the growing Internet. Now let's talk about subnetting. Subnetting is just a way to split a big network into smaller parts, called subnets. Imagine your network is a big pizza. Instead of giving everyone a huge slice, you cut it into smaller slices so it's easier to manage. Every device on a network has an IP address, which has two parts. Network part shows which network it belongs to. Host part shows the specific device. Subnetting takes some of the host part and uses it to create more, smaller networks. This helps organize the network, improve performance, and make it more secure. Now, we'll explore MAC addresses and how ARP helps devices talk to each other. A MAC address, which stands for Media Access Control Address, is a unique identifier assigned to every network device, like your computer, phone, or printer. Think of it as a name tag for each device on a local network. It helps the network know exactly where to send data, so your messages and files reach the right device. Next, let's talk about ARP, which stands for Address Resolution Protocol. ARP is a network protocol that helps devices find each other on a local network. Specifically, it maps an IP address to a MAC address, so your computer knows exactly which device to send data to. Think of it like asking, "Who has this IP address? Show me your name tag," and the right device responds. Next, let's talk about ports and protocols. A protocol is a set of rules that devices use to communicate over a network. It's like a common language that everyone follows. A port is a numerical endpoint on a device that identifies a specific service or application. Together, protocols and ports make sure your data reaches the right place on the right device. Let's talk about TCP and UDP protocols and how they help data travel on a network. TCP, or Transmission Control Protocol, is reliable and connection-oriented, which means it makes sure data arrives correctly and in order. It's used for things like web browsing, remote access, email, and file sharing. For example, HTTP, port 80, is for regular web traffic. HTTPS, port 443, is for secure websites. SSH, port 22, lets you securely access devices remotely, and RDP, port 3389, is for remote desktop access. TCP also handles email and file sharing. FTP, port 21, for file transfers. SMTP, port 25, for sending emails. POP3, port 110, and IMAP, port 143, for receiving emails, and SMB, port 445, for Windows file sharing. On the other hand, UDP, or User Datagram Protocol, is faster but connectionless, so it doesn't check if data arrives perfectly. UDP is great for things like network services and time syncing. For example, DNS, port 53, resolves website names to IP addresses. DHCP, port 6768, assigns IP addresses. SNMP, port 161, helps manage networks. NTP, port 123, synchronizes clocks. And TFTP, port 69, transfers small files quickly. In short, TCP is reliable, UDP is fast, and both use specific ports to make sure data reaches the right application on the right device. Next we will explore, what is DNS? DNS stands for Domain Name System, and it's like the phone book of the Internet. Every website has an IP address, which is a string of numbers that computers use to find each other. But remembering numbers like 123.254.123.3 is hard, right? That's where DNS comes in. When you type a website name like www.google.com, DNS translates it into the correct IP address so your device can connect to the website. Simply put, DNS helps your computer find websites by name instead of numbers. Next, we will talk about Dynamic Host Configuration Protocol. DHCP stands for Dynamic Host Configuration Protocol. It's a network protocol that automatically assigns IP addresses and other network settings to devices on a network, so they can start communicating right away. In short, DHCP is like a helpful assistant that makes sure every device gets its own address without any conflicts. Let's see how DHCP actually works between a client, your device, and a DHCP server. When a device joins a network, it doesn't have an IP address yet, so it sends out a DHCP discover message, basically saying, "Hey, I need an IP." The DHCP server receives this and replies with a DHCP offer, suggesting an available IP address and other network settings. The device then responds with a DHCP request, saying, "I accept that IP, thanks." Finally, the server sends a DHCP acknowledgement, confirming the assignment. Now the device has an IP and can communicate on the network. At last, let's talk about network address translation and port address translation. NAT, or network address translation, is a technique that lets multiple devices on a private network share a single public IP address when accessing the Internet. It's like a receptionist forwarding mail to the right person in an office. PAT, or port address translation, is a type of NAT that keeps track of which device is sending which data by using ports. This way, many devices can connect to the Internet at the same time without confusion. In our next video, we'll explore how all of these networking concepts, IP addresses, subnetting, MAC addresses, ARP, DHCP, DNS, and NAT, fit into the OSI model. Thanks so much for watching. If you found this video helpful, don't forget to like, subscribe, and hit the bell icon so you don't miss the next one. See you in the next video.